I have just redrawn all the 14 states, these were the same which I used last time. So, because we need to keep on referring it, so I have just
when you calculate the probability, so you are considering half and one when state are merged or the number of packets are there. Sometimes
the formula which I wrote last time. I had not explained that, I think. I left. Some of you might have intuitively figured it out how it happens. So maybe I can explain how that formula comes. So I will start with that itself. That was Pj tilde. That's what we were computing. This was probability that a packet at switch output link in stage J will be passing out in time tau k. Okay. So let me write down the expression and see how that will get derived actually. So this was Pj tilde which was there. This is the probability that a packet at switch output link in stage J passed actually forward in time interval okay, and this is basically a conditional probability. It is conditioned on that the packet has to be there at the output of jth link. So there has to be a packet first and then it will be transferred on to this thing. So remember the step 1 is when this packet goes out, okay, and after step 1 the packet has to jump actually from here to here. So this one was basically after step 1. So after j plus 1, if the packet on the outgoing link has gone out, that is step 1 is over. After that step, what is the probability that it will be in which state? That will decide what is going to happen in step 2 here, and that in turn will decide what will happen in step 1 here. So if you remember the diagram, step 1 when it happens here, step 2 is happening at this point, okay, and step 3 is happening further. That is what was usually the case. So whenever the step, I think I had drawn this figure that time, 2 specific cases when I defined step 1 and 2. So when there are 2 stages, so when this packet is going out, so here it is happening step 1. The packet is jumping, so step 2 is happening here. Okay. For this packet is arriving at the input link, so step 3 is happening here. Okay. Step 3 packet arrives in your input buffer, step 2 packet goes from your input to output buffer, step 1 packet goes from your output buffer to onward.
Step 1 the packet goes from output of j minus 1 to output of next state.
Whatever is your stage, from your output the packet should be moving further. That is your step 1, and once your output link is free, then only from your input to output link a switchover will happen. That is the step 2 for you. And once your input link is free or available, that buffer on that, then some packet from the previous stage can come in. That is a step 3 for you. Okay. So basically when this movement will happen will be decided by after step 1 in which state this particular switch is. So I have to look at all those possible states where there will be a packet here at the input. Now since actually this the way it will be is, I have to look at now basically, because this is a conditional probability that first thing the packet has to be there. So I have to now sum up all the state after step 1, what are the states, all possible states, because state probabilities are absolute probabilities, these are not conditional ones. So, find out all possible states and sum up all the probabilities combinations by which a packet will be here at this place. So, if you look at for example, state 1, there will not be any packet here going out. I have to look at only those states where this packet will be there, and then I have to find out whether packet can move on the other side or not. So, for example, if you look at 2, there is no packet at the input, this cannot be counted, 3 cannot be counted, 4 there is a packet here. The question is, you might be connected to this link or you may be connected to this link. So, probability that this is in state 4, you have to multiply by half, with only half into being in state probability, being the probability of being in state 4 multiplied by half. With that probability you will have a packet here, and with remaining half multiplied by the same probability, the packet will not be there. I have to list only those situations or those probabilities where the packet is available here. Okay. Then I have to now sort out those conditions where the packet can move from this place to this place in step 2 when the step 2 will be running here. So, after step 1, what is the current state that itself governs what is going to happen in step 2. So, after step 1, if you are in this state, so after step 2 this packet will be going out. So, that should be there in numerator because of that. Okay. Look at this situation, with half into probability of being in state 5, you will have a packet, half into the same probability you will not have the packet. But when you have the packet, this packet cannot move further in step 2 because this is a state after step 1. So, there will not be any movement. So, this should not appear in the numerator. So, I am looking into absolute probabilities in the denominator, multiplying by the probabilities when of those states where packet is going to move out in step 2 in J plus first stage, because your condition is after step 1 in this stage. So, what is the probability that in step 1 packet will move out? That is what we are saying is Pj tilde. Okay. So, we have to essentially do this enumeration. So, I think for clarity's sake let me just write down this expression, but this time building it step by step. Yes, last time I did it in hurry, I only did it in the end of the lecture. Okay. So, today we have time, so I can do this, and remember this is a conditional probability, that is why I am doing it. Now, look at 1. 1 should not be listed in the denominator, 2 I think should be listed or not, no, 3, what about 4, yes, and half of it or 1 of it, half of it, right. So, it is half, and what I should write, its probability after step 1, okay, and what is the state 4, okay. This I am talking about J tilde, so this is J, so this should be state for J plus 1, okay. So, I am going to write J plus 1 here, and then of course, this is in time tau k, so I have to write k in on top of it after time step k, T k. Now, with 5 what should I write? Half, agreed. Now, go to 6, half of being in probability of 6, now moving over to 7, again half, 8, it has to be full probability of being in state, 8, what about 9? All are full, so I am going to write all of them. So, only these many states have to be included in the denominator. Now, let us look at the numerator. When the packet will move out, I am looking at P A tilde, conditioned on that the packet happens. So, these states will actually give you essentially 1 over this technically gives nothing but probability that this is actually all possible states which. So, this technically gives nothing but probability that your packet is here 1 over that.
Input of j plus 1.
Input of j plus 1.
Yes, right.
Sir, step 1 in jth state, sir. Step after completing step 1 in jth state.
J plus first.
Step 1 in J
I am looking into the state of J plus first block or switch in J plus first stage after step 1. See, then only I will know okay, what was the state after this, okay, what will happen in step 2. So, this is situation after step 1. Now, I am going to look into what can happen possibly after step 2. So, if you look at step 1, that is state 1, nothing is going to happen, that state is not of our interest, there is no packet. So, it cannot contribute to the probability that this packet will be there. See, technically what happens is you will have always P conditional, the packet has to be there. And there is a conditional probability that packet will pass. So, absolute probability when you multiply by that, when packet probability that packet will be there. This conditional probability is coming from here actually. So, this is probability that packet is going to be there. The above one gives the absolute probability. So, absolute divided by this thing, this is like probability that packet will pass divided by probability that packet is going to be there. So, this is absolute probability, you have to divide by the probability that packet is there, that will give you condition. So, that is why there is a probability that a packet is present at the output of jth stage, that is why I have written that thing in denominator. Because what I am going to write in numerator is nothing but absolute probability of packet being going out, but I want to have a conditional probability instead of that. Okay. So, look at state 1 cannot come here because there is no packet can move out, so it cannot contribute. Packet 2 there is no packet, so packet cannot move out, it will not be there. State 3 no, state 4 packet will move to the second step, the output of j plus first. So, j plus first will be executing, when it goes through second step this movement will happen, and then the step 1 will be happening in jth stage. So, here step 2 will happen, see it will be like this. So, step 1 has already finished here. So, now when the step 2 will be executed, this will be moving on this side, and then that time there is step 1 will be running here. That is what this Pj tilde is about. After step 1 packet moves out. So, after step 1 what was the state will decide what will happen in step 2. So, that is why I am going to write in numerator the state probabilities after step 1. Okay. So, 4 will contribute, and how many times? With half probability only it will happen, because I may be connected to this link or this link. If you are connected to this link, there is no packet going out. When you are connected here, then only packet is going out.
The state and merge here. The two state and merge here. It could be considered.
Yeah. So, I am all equivalent states are being represented. See, no one state can be mapped onto another state by any kind of rotation, flip or whatever it is. That has been ensured.
That's why, sir.
Yeah. So, you will have half of P after 1, 4, j plus 1, k. Now, look at state 5. Even if after step 1 in this particular stage you are in state 5, State 2 when is going to be executed, step 2 is going to be executed, packet cannot move because one packet will be present here. So, this cannot contribute to Pj tilde. So, I should not put it in the numerator even when packet is present actually at the output port. So, 5 will not contribute in the numerator. Look at 6, packet will move out after step 2 in j plus 1 and packet will be emptying the outgoing buffer after step 1 in jth stage. So, that has to be included, the 6th one, and that will again happen with half probability because I can be connected to either of the two links, input links. Fine. Look at 7, no, packet can't move out, so it should not be listed in the numerator. State 8, only one will move out and you can be connected to any one of the input links with equal probability, 50% chance it will move out. Remember, this one is 8th one is listed with full here, it is not half in the denominator, but in numerator it will become half because only one packet can go out, not both. So, I will be listing ninth, both of them will go out with 100% thing. Okay. So, it is there is no half here in this case. 10th, nothing will go out, so it should not be listed. 11th, only one will go out. Okay. So, it will be half. Not 10th, this has to be 11th, sorry. 10th nothing can go out. 12th, again only one can go. 13th, nothing can go. 14th, nothing can go. So, those will not be included in the numerator. So, this gives you Pj tilde. So, I think now this is more clear in the second iteration. Last time it may not have been. And most important thing at the end, the last link, last stage. Since remember now what the case which we are looking is when T select is 0 and sorry T pass is 0. That actually means when two packets are there in the last stage and they are both can go out, this buffer will always be empty because packet transmission takes 0 time, is instantaneous. Even if both have to be switched out, they both can be read instantaneously and taken out of the buffer. So, what will happen is this is n minus first stage or n minus 2 because we have 0 to n minus 1, sorry. So, it means Pj Pn minus 2 is 1.0, that is a boundary condition. So, when we will iteratively do the solution, this will be the boundary condition. In any stage Qj will be defined as Pj tilde. If Pj is probability of packet going out, Qj is it will not go out, it will remain there. Okay.
Only one boundary condition, that is.
Yeah, I am now coming to the other formulation also. So, all of them will be used continuously in tandem. Then I will give the process, the method. So, I have to give all this, then I have to give transition probabilities, and then I have to give the method which has to be executed. This all is done in a computer program, it is not a simulation, it is a computation, but it is an iterative computation, it will converge at some point of time, and when it converges that time you take out all the results and find out the throughput. So, that is the procedure, there is no closed form solution. Okay.
Any reason you write 1.0? Any reason you write 1.0?
You can write 1, not an issue. Probability cannot be. So, somehow we always write it as 1.0.
This probability, both T pass and T select are present in this probability.
T select, T pass is 0. T select is complete what we call T delay.
So if T pass is 0, then 8th state, those 2 packets can be sent outside, right?
Depends on in which state you are, in which stage you are. If that's the last one, see for example these states cannot exist where the outgoing ports, outgoing packets are there, these states cannot exist in the last stage, because outgoing will be immediately emptied out. Okay. This will, and in n minus 2 stage this is going to be there for some time, okay, because when this is selecting, these packets have to be held here. Once the T select is finished, then only they will be removed. So you can actually have these, all the states are possible at n minus 2, but in n minus 1 only this state is possible, this state is possible, and these 2 states are possible. No other thing will be existing. No other thing will be existing. So 1, 4, 8 and 9, that those are the only possible states for the switches in n minus 1 stage. From there we will do, I will actually tell you how this backward calculation is done.
So when you think this is a computation process, it will iteratively.
Yeah, it's an iterative computation process, that's the only way.
Between this computation and simulation.
Simulation, what you will do is you will actually create, you will actually generate packets, you will let the packet flow through. See, it will be like kind of, you will have a clock, a universal clock. At first clock there are no packets, then the clock goes from 0 to 1, you will generate packets at the input, and then what happens in that clock, you will do find out the whether conflict is not there or not there, you will actually move the packets. You will maintain a data structure which will maintain the complete state of the switch, and now this state will be evolving on the basic principles, and you will keep on moving. Ultimately at the output you will observe how many packets have passed successfully. Now you have to observe for multiple clock instants. There is nothing like what we call a time after which you find out there is a convergence. There is nothing like convergence there. And in simulation there is another very tricky thing. Here I will just look for stabilization. When convergence happens, I will just take the results in this computation. In simulation there are no packets, so it is not a steady state. So initially there will be a transient. So I will discard that actually, all that observations, and after that I will observe per unit time, per unit slot how many packets are successfully going out. I will keep on making observation. I will observe for certain number of time slots. It is like you implement actual switch, but not in actual reality, but in computer program. So you are simulating the algorithm itself, not computation algorithm, but operational algorithm by which they are operating. Okay. So whatever is that Petri net, that essentially you will be implementing there, or equivalent of that. But the paper does not talk, the actually paper do have simulation results which are matched with the computational result. These are very precise. It is like I ask you what is the, how you will compute the value of pi. Okay. So one very simple way, how you will do it through simulation? Now, can anybody tell how you use simulation to generate the value of pi?
We keep on drawing circles and keep on taking the ratios. And we give simulation.
No, that's a different thing. By simulation, Monte Carlo simulation. Can anybody think?
We have circle of radius r and then r arc length.
No, that is fine. That you know all by mathematics. You don't need to remember. You only need to remember that the area of a circle is pi r square, and area of a square is r square, and you always know that if I make a square, I can always create a something like this. So what is the area? 4r square for the square. Circle has the area of pi r square. So what is the ratio?
4 by pi.
Pi by 4. Suppose circle to this thing. Write a very simple program. With uniform probability I do a coin toss and I put a point. Okay. So I choose a random number generation and the points will be just randomly plotted. You put 1 million points. how many fraction of points will be there inside the circle and how many will be total points which are plotted inside this. So, find out the fraction which lies inside the circle, and that fraction most likely will be nothing but pi by 4. And once you know that fraction of points which are there inside the circle multiplied by 4, that will give you value of pi approximately. So, this is a pi measurement through simulation, this is not computation. So, I think now you understand what is the difference between simulation and a computation. Otherwise, you write a series thing and do it, or do whatever calculations, draw circle, make length or whatever it is, that is a computational process. But pi, there is a closed form solution, no, it does not exist. So, closest approximation is 22 by 7, which is we all know, that is approximation. But best is draw a circle, measure the length, find out the radius length, take the ratio, and that is the value of pi. Larger the circle, better will be the estimate. So, that is a computational procedure. So, I am not still simulating, you have to understand, this is still a computational procedure. Well, students do have a tendency of mixing up the two things. So, usually simulation is nothing but whatever happens in real life, from those observations you make an estimate. That real life experiment is actually simulated in a computer program. Is conducting an experiment in a computer program, through a computer program, and then from there making observation. So, usually random number generation will be part and partial of any simulation process. I am not doing any random number generation here, so it cannot be simulation, and there is no statistical estimation. Okay, so this is a computational procedure. So, paper actually does give both results and they actually match pretty well. So, this seems to be a logically right way of getting the solution. This is nothing but a iterative method of getting to a solution of a Markov chain, which I explained earlier in the last class, where I gave it for a Markov arrival, Markovian departure and single server queue with infinite buffers. So, how we can get a solution to that? So, it will essentially convergence will happen, and that time you get all state probabilities. So, for all complicated Markov chains, I think this is a very good method. And here what the nice thing which has been done is, how many switches are there in a stage, those are immaterial. How many stages are there, those what matters. So, all state probabilities within a given stage are all, for every switch it is going to be same, that is assumption. And we have built up the relation between state probabilities of various stages. That is what I am doing actually now. Okay. So, next probabilities which we need to compute is probability that a packet will, I have to essentially erase this. See, because remember state transitions, how it is happening. When I am looking at jth stage, when a packet is going out, state transition happens. Then from there, from my input link to output link, there is a packet movement, that is a step 2. Step 3, when the packet will come from the previous stage. Okay. So, I have to look at the state transitions. So, this first transition after step 1 in this thing happens as per this relation P A tilde, it depends on that. So, if the packet moves out or does not move out, we will decide what will be the state transition matrix here. So, if what was the state at t is equal to 0 or just before the first step, and what happens after the first step. First step is this moving out when this has a step 2. Then once we know what happens if the step 2 is run. So, if I know the state after step 1, whether packet is there at the input, what is situation at my output, that will decide. And once if I am available, what is the chances the packet will come from the previous stage, that will decide for the step 3. Okay. So, this is for that situation. time interval tau k. So again I have to write down all the state probabilities.
This will also be called Pj tilde. This also will be called Pj.
Pj bar. Now it is not Pj tilde, it says Pj bar, sorry. So now what is happening is, this is the situation. Okay. So I am now looking at the states here, and step 3 in step 2 is running here, and what happens in the step 2 will decide what will happen after step 3 here, and what will happen in step 2 will be decided by what was the state after step 1. Okay. So now let us look at it. I am trying to find out what is the chance that a packet will come from this input to here. So after step 1, if this j minus first stage in state 1, can a packet come here? First thing I have to find out, I am having an empty state here, there is no packet. I have to look at only all those possible states after step 1 here. Then only I can figure out what will happen in step 2.
But first you have to check whether packet is there or not.
Packet should not be here. So step 1, state 1, no packet at the outgoing port, so it is free. So I have to list that actually.
So, but step 1, the packet will be sent out from the output port, no, sir?
Which one?
After step 1. So for step 2, output port will be always free, no, sir? Because in step 1, whatever the existing packet is already sent out from the output.
No, that can only be sent out. It is possible if you look at earlier case. Sometimes packet cannot be moved out again after step 1. If there is a packet in the next buffer, you cannot just simply push. You have to just keep on waiting. You have to just keep on waiting. So after step 1, what are those states where this port is free? I have to look at those. That has to go in the denominator. Numerator will be those probabilities of those states where the packet will move from input to output of j minus 1. So
In
look
this
at
case,
this.
We will not consider anything which is not available. I mean, packet has to be there. There is a probability of that also in the input stage. Shall we not?
I am only looking at the relations as of now. Okay. After step 1, what is the state here? That will decide what will happen in step 2. Because when the step 2 will be running here, step 3 will be happening here. I am looking at the probability after step 3. Okay, probability that a packet will arrive in the input buffer. This can only happen, this will be decided by what happens after step 1 here. What is the state? That will govern the computation of this probability. So after step 1, if there is a state 1, j minus 1, this is important. Both of the outgoing links are free, and I can connect. This is the, remember earlier case was like this. We are sitting here in jth stage, so we are looking at j plus 1 at that time. We are looking in the backward direction. Okay. So with probability 1, I can be, both of these links can be connected to me, is not half, so both with equal probability, so both times it will be empty. If after step 1 this has a, if after step 1 this is in state 1, so I will write this. State 2, half, because there is a half chance, because this is in, after step 1 you are in state 2, so you can be here or you can be here, packet can be any one of the two. So with half probability you will actually may get it empty or may not get it empty, and if it is not empty the packet cannot come, it has to be empty first. So I will write now half of P1 to j minus 1 k, P3 P3 should not be there, because then my input buffer link itself is not, input buffer is not free, it is already occupied. Okay. So no packet can come, so it cannot contribute. 4, yes, it is there, and 4 means both. So P1 4, there is no half in this case. State number 5, half. State number 6, again half. State number 7, no. State 8, full. State 9, full. State 10 is half. State 11 is half. State
10
Sir,
will be half. 10
huh?
10 also will be half, multiplied with half.
10 will be half, right. 11 also will be half, na? 12 also will be half. No, 13, 14 cannot be half, they cannot exist. Yeah, we got everything right here. The upper ones we have to look. State 1 packet cannot come in, packet cannot go actually in step 2, there is no transition possible, so this cannot contribute. Packet state 2 cannot happen, state 3 is anyway not possible, state 4 yes, if the switch at j minus 1 is in state 4, after step 1 in step 2 packet will transition, so this will contribute to Pj bar. So that has to be listed, but this will be happening with half probability, because your switch can be connected to any one of the outgoing. Okay, so it will be half of P14 j minus 1k. Okay, P5 no, there is no possibility. If you are in that state, packet will not come in. Packet 6, yeah, state 6, this is going to happen with half probability. Then after 6, 7, nothing, 8, you will get with half probability a packet. Okay. While in the denominator it must be actually full probability, because both outgoing links are free. Ninth, yeah, it will be full. 10, nothing will be there, no packet can come in. 11, yes, packet can come, it will be half. 12 also will be half.
Why should 8 be half, sir?
Both are going to same also.
But both cannot go simultaneously, only one of them will be coming.
It has got absolute probability that it
No,
will
the question is,
in output.
you can be either connected to this or you can be connected to this with half probability. Na? See, jth switch is connecting to j minus first.
Yeah, understood.
So if you are connected with half here, you will get a packet. If you are connected here, you won't get a packet.
Understood. Understood.
Okay. So that's why this is listed. Now with this thing, this is, remember what is happening is, this is transitions after step 1, this tells what is going to happen in step 2 essentially. So I am looking into arrival probability here, so what is going to happen in step 2, I am looking at that. Now for this the boundary condition will be P0 bar means the first switch, the input of that, I am looking at a maximum loading condition. If this is free, then the probability that arrival will happen is 1, that is a maximum loading condition. Again sorry, I can write 1. And of course Qj bar 1 minus Pj bar, that condition will be there.
Sir, in this denominator 1 by 2 P5 state, how is it? Denominator.
This one. Look at the fifth one. See, you can be connected here, then your switch was state that buffer was not empty. So that should not be counted. With half probability you will be connected and you will have a buffer which is empty.
If it is connected like that, it will be 60.
Conditioned on that it in jth stage my switch input is free, there is no packet there. On that condition, what is the chance that packet will arrive in step 3?
Actually in state 5 sir, step 1 has not happened in J minus 1. In state 5 sir, step 1 has not taken place in J minus 1 stage.
Does not matter. I am looking at after first stage whether what is the chance of being in this state. If you are in this state, this is free, but no packet will be transiting. This is not there in numerator, this is only in denominator. So I am looking at what will be probability that a packet will be arriving if my input is free. I am estimating that. So this contributes in the denominator only 50%, when that input link will be free. For that, it is contributing to that actually. It is not there in numerator. Now let us come to the state transition tables. These two things essentially we will be handling. I'll try to build everything here. This figure still has to remain there. So I call this transition matrix as Tj. In the jth stage, this is after step 1, going from initial stage is m and you want to go to initial state is m and next state is I after step 1. Okay. So I make the probability is going to be 1, 2, 3, these are the states. Only 14 are required, sorry. Okay. So if you are in state 1, what will happen after step 1? There is no packet or outgoing thing, so there is no question of it is going out with certain probability Pj. So with probability 1 you will remain in state 1 only. Okay. So we will keep this as 1. So I am going to put only the values which are existing, rest everything is 0. Okay. I am not filling up all the cells here. All other cells will contain 0 except the way where I have written the values. Now look into state 2. State 2 will remain, now the probability that that packet which is sitting there goes out is Pj tilde. So if that packet goes out, you can come back to state 1. If that packet remains there, you remain in the same state. Okay. So it actually means this will be Pj tilde, no, this should be a Pj tilde, you will come from 2 to 1, you will remain in 2 with Qj tilde, rest everything is 0. Not clear? So you have a switch, and if it is in state 1, this is a state 1, and what is step 1? Packet from at your outgoing port goes out, and if you have a packet here, this will go out with probability Pj tilde, and it will remain there with probability Qj tilde, which is 1 minus of Pj tilde. In general stage, because if it is the n minus second stage, packet will certainly go out, there is not an issue after step 1. Okay. And if there is another one, so this will be going independently with Pj tilde. I am only talking about one packet condition if the packet is there. If there are 2 packets, both of them will go out, what is the probability?
Pg tilde into square.
Pj tilde square. Only one of them goes and one of them remains. Multiplied by 2, there are 2 possible combinations. Both of them remains there, Qj tilde square. And all these 3 events will lead to certain state transformation. So if there is no packet, here, with certainty, with 100% probability or 1 probability, it will remain in state 1 only. That is what I have written there. So this is your M, and this is your M to I. So M to I transition. This is the initial state, this is the next state after step 1 in jth stage. So this is the transition probability in jth stage after step 1 for going from mth state to ith state. Okay, so you can actually write going from state M to state I in jth stage, okay, after step 1, and this is nothing but the probability, and this is what is this transition. You build up the matrix, you find out from each state to other state what is the transition probability. So 1 to 1 is obvious actually. If you are in state 2, you will have only one packet sitting here. If this packet goes out, what is the probability of it going out? Pj tilde. So if it goes out, in which state you will be? State 1. So I have written here Pj tilde. From 2 to 1, this is the probability that you will be transitioning. And 1 minus of that, packet will not go out, you will remain in the same state. If you remain in the same state, that is what I have mentioned here. And remember, rest all these blanks will be 0. You cannot transition from state 2 to state 4, for example, that is not possible. Look at state 3 now, which contains 2. So with probability, as all of you have told, Pj tilde square, both the packets will go out, you will come to state 1. So you write here Pj tilde square, and if of course only one packet goes out and one remains, you will remain in state 2. So that is 2 Pj tilde and Qj tilde. Of course this is very small, so maybe I can write it. Here.
Sir, why factor of Q will check?
Each event is happening independently. There are 4 possible cases, na? There are 2 possibilities here and there are 2 possibilities here with equal probability. So one case is Pj happens, other says Pj happens, here Qj happens, here Pj happens. Okay, here Pj happens, here Qj happens, and here Qj happens, here Qj happens. Each possibility is 1 by 2, 1 by 2. So these two are same, they always lead to the same state. So that's why 2.
Actually, the tabular descriptions are of Markov chain. Tabular description.
Is a transition probabilities. Still Markov chain has two things, the state probabilities and then transition probabilities. Markov chain has these boxes, so there is a probability of being in here and this is the transition probabilities.
But we can do the same thing with
That is
bar.
what we are doing tabular, sir. This transition. That is.
No, because I am not actually making any Markov chain. Yeah, technically yes, I am doing the same thing. You are right. Technically I am doing the same thing.
We'll also have a transition matrix for that bar state, PJ bar, similarly, which you just derived now.
A transition matrix.
Yes, sir.
It will come. This after step 1. I have to draw TJ2 also, TJ3 also. There are 3 matrices which will be there. They have to be maintained as data structures during your computation. Simulation is far simpler actually, remember. If you want to write a program for simulation, that is going to be simpler than this. But the good thing is that you do not have to remember all the possible switches which can exist in a single stage. Okay. So only states you have to take care, and you have to take care of stages. State to state actually transition will be there. And of course Qj, you will, both of them will be remaining there, so 3 to 3. Qj tilde square. So fourth will be similarly, if you are in fourth one, then what will happen? After step 1, step 1 is packet from your outgoing port goes out. There is no packet at the outgoing port, so nothing will happen after step 1. Only step 2 can make a transition in this. Step 1 cannot make any transition in this state. So this will remain in the same state. This cannot do anything. So 4 will remain in 4 with probability 1. 5 with probability Pj, this can be converted to 4. With Qj it will remain there. That's it. Okay. So with 5 can be converted to 4 with Pj thing, and with remains 5 with Qj tilde. This is sparse matrix actually. Sixth, same way. After step 1, packet can go out or packet cannot go out. So if the packet goes out, this becomes nothing but 4, otherwise it remains 6. Okay. So it is, if it goes out, it will remain Pj tilde, 6 it will remain Qj tilde. Of course, it's all. Seventh state, this can be converted to 4 Pj square, 7th if it is there, Pj tilde square, and if one of them goes, either 5 or 6, 5 or 6 with equal probability, 5 or 6 with equal probability. Okay. So you have to write Pj Qj tilde, Pj Qj tilde. This has been, remember the complete row when you sum up has to be equal to 1. Okay, sum across all the rows has to be equal to 1. And of course then Qj if you have, it will remain 7. Eight, what will happen? 8 will remain to 8, not an issue. 9 will remain to 9. 10 will become either 8 or 10 will remain 10. So 10 will remain, 10 will become 8 with probability Pj tilde, and 10 will remain 10 with Qj tilde. 11 will either remain 11 or will become 9?
It will be 8 in 10 row.
Column 8.
10 row 10 row. It should be 8 column. PJ tilde.
ओ कहीं गड़बड़ कर दिया है मैंने, 8 यहाँ पे ना, ये गलती हो गई.
And 7 P also.
P also has to go to
8 column.
रुको
Same row 8 column.
हाँ 8 में जाएगा. राइट गड़बड़ हो गया भाई. Same way you can do with 11. 11 goes to either 9 or ठीक है. 11 either become 9 or remain same. 12 will either remain 12 or will become 8. Thirteen. There will be 4 entries for this. So either it will become 8 with pj square, and pj qj, either it will be 12 or 10.
9,
Or 10.
10, 12 with equal probability.
Or 8.
Okay, 10 and 12 pj qj, and of course 13 if none of them goes.
So it can be 9 also. 9.
How?
No packet.
13 cannot go to 9. Same directions, no? Same port. See, direction you have to always take care. 13 cannot go to 9. 13 only can go to 8, can go to 10, or can go to 12, or remains to 13. 14. 14 can go to 9. 11. 14 can go to 9.
11 with 2 pk.
या 11 में 2 बार हो जाएगा. राइट. 14 can go to 9. Where is 9? Yes. It is 2 pj qj tilde. So that's a complete transition matrix. Similarly, you can draw the transition matrix for after step 2. Now, important thing, if you have this, okay. So after 0 step, you know the probabilities. This basically is the beginning of the slot. Okay, you can multiply it by now transition probabilities after T1 J Mi sum over all probabilities I think now you can appreciate. If I know the state probabilities in state J after 0, I can compute from there my state probabilities after step 1. Okay, and these are the transition probabilities which will come, and transition probability is now depending on. Okay, so this here where I am actually finishing. Next we will look into the next state transition diagram, which is after step 2, and then step 3 and so on, and then actually the method of calculation. Okay, so that we will be covering in the tomorrow's lecture morning.